So, hi there, welcome to the lecture on discrete logarithms and elliptic curve cryptography. So we're continuing a bit today what we started already last week, namely with, last week we already had a look at some asymmetric cryptographic schemes, in particular based on the problem of factoring. So factoring was the underlying hard problem, and we saw that this is already quite useful. We can build encryption schemes from it, we can build signatures from it. We had a look at some of the maths which we just recapped in the exercises. However, the plan for today is to look at a different hard problem that we use as a basis for our crypto systems, and we will see that this has a number of advantages. And the hard problem we want to look at is the discrete logarithm problem and its variants. Now, to look at that and to take full advantage of it, we will need some more math background, particularly finite fields, but also elliptic curves, because we will see that the schemes that are based on the discrete logarithm problem come in two main flavors: those based on finite field cryptography, such as the DiffieHellman you might already know, and the variants based on elliptic curve cryptography, which have very similar algorithms. So the structural properties of these are quite similar, but the specific arithmetic operations that you execute are quite different. And we will see that this version here has some advantages, but it's a bit harder to understand. And this is the second out of 3 lectures on asymmetric primitives, because next week you will have a look at post-quantum secure asymmetric primitives. So in some more detail, what's the plan for today? We will first have a look at what finite fields are and how we can define them and how we can use them in crypto. And second, we will introduce the concept of cyclic groups, which is based on the stuff we already heard last week, but we will need some additional vocabulary. And then we have these 2 main parts. First, the general discrete logarithm-based crypto, in particular the stuff based on finite fields, such as the classical DiffieHellman algorithm or the DSA digital signature algorithm. And afterwards, we will see how we can carry this over to a different mathematical structure, namely elliptic curves. And we will see that most of these algorithms here have an elliptic curve counterpart. And we will discuss what the advantages and disadvantages of this are. I see there's already a question at this point, I think. Are the slides available somewhere? Oh, damn it, I forgot to post the link. If you wait a second, I will post the link in the description. Sorry, I forgot about that. This will take a second. So the link to the slides, to the handout version of the slides, should now be in the description of the YouTube video down below. If you can't find it there, send me another message and I'll have a look. Okay, so that's the plan for today. So let's start at the beginning, namely at some more background. And this is because the stack of math ingredients that we will need will grow quite a bit today. What we've already seen so far, or what you already know, is of course you have known for a long time how to compute with integers. You have already also known for quite some years how to compute modulo a prime number, and we recapped it last week. So this is sort of the basis where we are, and the good news is that where we are so far is already sufficient to describe some of the crypto systems, namely basic DiffieHellman and digital signature algorithm, for example. However, it is not sufficient to describe elliptic curve variants. So for these, we will first need to introduce what an elliptic curve is, based on prime numbers, but we will also see that there is a second type on elliptic curves, which is called binary elliptic curve, because the underlying size is a power of the number 2 instead of prime numbers. So the underlying field size. So for this we will need to introduce how finite fields over a prime power work. So that in the end we have two types of fields, those with a prime number of elements and those with 2 to the something elements. So this is the stack of structures that we need. So let's have a look at what fields actually are. You may already have heard that term somewhere in your math lectures, because a finite or a field is quite a logical extension of groups. We've been talking about groups last week. Groups were a set of elements with an operation on it that has some nice properties. And a field is simply a set of elements with 2 operations based on it, like we also usually have it, for example, in the real numbers. Namely, we have both an addition and a multiplication operation. And those 2 operations individually need to have the same nice properties that we are used to from groups. Namely, the elements only with the addition are a group, with a neutral element 0, and the elements except for this neutral element with multiplication also form a group, which have their own neutral element, namely the 1. We've also already individually seen these groups last week. What's new, what makes them a field, is if they work well together. So if they have the usual distributive properties that c times a plus b is the same as c times a plus c times b. So in other words, we call them, they distribute. So this is the general definition of a field, which you probably have heard already at some point. A finite field is simply a structure that satisfies all of this, but where the number of elements is a finite number. So for example, the real numbers are a field, but not a finite field, whereas computing modulo p with the addition and multiplication we know already gives us a finite field, because we heard already last week that these operations individually satisfy our group requirements if the modulus is a prime number. So talking about the size of fields, it's supposed to be finite, we heard. And we already saw that we know examples of fields, namely fields with p elements, where p is a prime number, because this is the number of elements in Zp. And it turns out that this is not the only possible size of finite fields, but the sizes are still limited. Namely, the number of elements in a finite field is always a power of a prime number, some prime number p to some exponent, which is I think called n here. Yes, n. And we also have a special notation if we refer to the field with this many elements. Namely, we write it either using this mathematic double letter style f with a p to the power n in the index, or this is more in English-speaking countries, gf of p to the power of n, where gf is short for Galois field. Évariste Galois is a very famous mathematician who unfortunately died very young, and he laid a lot of the groundwork that this stuff is based on. So either of these 2 things mean exactly the same thing, and they mean a finite field with p to the n elements. So the question is, of course, quite obvious now: how do we build such a system? So we already know how to build it when the exponent is a 1, so with p to the power of 1 elements. But the question is, how do we do it with more? So what does a field with p to the n elements look like when n is bigger than 1? When n equals 1, we have this Zp that we already know. And the following, I'm using this notation with boxes when I mean I'm using one element from the set I describe in there. So if I take a set with p elements, then there are of course p options to draw from this. If I now want to somehow encode something such that I can draw, or that I can describe p to the power of n possible elements, there is a quite straightforward way of writing that down, right? I simply take n elements, each of which is an element of Zp, or some set with p elements. Because then the total number, so if I write this down as a vector, the total number of possible values of this vector is p times p times p and so on. in total p to the power of n many. So if I want to write down what the data type looks like or what the data structure looks like that I store a field element in, this is quite easy to decide. I simply take a vector of such elements. But the big question is now, how can I define the corresponding operations to make this into a field? And as in the case we've already seen, for addition it's quite easy to find a suitable operation on vectors that works, namely simple vector addition essentially. But multiplication is a bit more difficult. And actually, you already know a structure where we have the same sort of idea. We have a basic field. In this example, it's the real numbers. And we are trying to build another field from it, which has, well, I can't really say the squared number of elements of R because this is uncountable, but which consists of two such blocks, which is essentially a vector of two elements of the real numbers. And those are the complex numbers, where every complex number is written as some coefficient times the imaginary unit plus some other coefficient. And these coefficients are both real numbers. So what we did in the real numbers to make them into a bigger field which has nice properties, such as being able to solve all sorts of equations in there, is we introduced an imaginary unit. And then, how did we define multiplication in these things? Addition was easy. We simply added the real component and the imaginary component and the real component. But for multiplication, if you remember, you had slightly more complicated rules, which essentially arose when you take this and multiply it with another thing of the same form. Then you end up with some I squared, which is equal to -1. And this gave you a sort of rule how to transfer things that included a y squared, an I squared, back into something that contained only i's. So this is the sort of inspiration we want to build on, having a sort of imaginary unit and then defining the multiplication so that it makes sense. And in this case, the multiplication made sense because we had the extra rule that I squared equals -1. We will do something very similar here. So to write down the computation rules or to define them, we of course need some notation. So I'm going to label the individual vector entries. You will notice that there are n of them, which I labeled based on index 0. And I write the one with index 0 in the rightmost position. This is maybe a bit unintuitive, and if you look at some implementations, some of them also encode it the other way around. But the important thing is that I'm using these entries of my vector as coefficients of some polynomial. So I'm interpreting my stored vector of n elements as a polynomial of degree n-1 over some undefined variable x. So I interpret one of these elements of Zp as the constant coefficient, one as the linear coefficient, and so on, and the topmost one as the coefficient of x to the n-1. And I guess you see now why I ordered them this way around. This is because I prefer writing down my polynomials this way with the most significant exponent to the left. Okay, so we're interpreting things as polynomials, and the x here is playing a similar role as the I was playing in the complex numbers. We are never going to put any sort of number in, like you never instantiate with I with something else. I is already something, it's a formal variable which has an extra rule, namely that I squared equals -1. And the same thing here, we are never going to plug any numbers in for this. This is just a placeholder that gives some mathematical meaning to the elements of this vector here. So let's have a look at some example computations where we're looking at the numbers modulo 2, because this is the easiest case. So if we're looking at examples modulo 2, for example, I've written down here an element with 8 entries each of them modulo 2, so either 0 or 1. So this would be a representation of one element in f 2 to the power of 8, because there are 2 to the power of 8 possible values to fill in these boxes. And this is another element of the same field. And for addition, I do what I already announced earlier, namely, if I look at it in the vector way, I'm simply adding up all the vector components, so it's normal vector addition. If I look at it in terms of the polynomial interpretation I defined earlier, this amounts to the same thing. So if I look at it in polynomials, 1 plus 1 equals 0 modulo 2, 1x plus 1x equals 0x modulo 2, and so on. So you'll notice the bottom row is simply the XOR of the two upper ones. And this is already everything you need to know essentially about the addition rule for our finite fields. Namely, it's simply an element-wise addition of the two inputs. This is very easy. Now maybe some bonus questions. Can somebody tell me what they think the neutral element looks like in this field? So how do I need to fill in these boxes here in order to make it a neutral element with respect to this addition? Maybe somebody can write an idea in the comments. Oh, come on. I guess at least half of you already know what the neutral element could be. We got a cat reaction, but unfortunately no reaction to the question. That's unfortunate. Let's see if somebody wrote something in the questions. No, nobody did. Okay, then I guess I have to answer that. So what would this second element have to be? Oh, something did just happen. Let me check. Somebody gave a very minimalistic question, namely the question 0, and this is indeed also the answer at this point here. So indeed, indeed, if I fill all my bits with zeros, then I have a neutral element. So if you imagine that I leave the first one as is, and I leave the second one in with all zeros, if I XOR 0 to something, it stays unchanged, meaning we have a neutral element. Next question is, what do inverses look like in this field? So if I keep the same first element, what do I have to add to it to get 0 at the end? You're all very shy and doing it the anonymous way. I was hoping to get rid of all the copies of my name up there. Let's see. The inverse is the same as what people suggest, and indeed this is correct, because if I XOR something to itself, I get 0. So the inverse of 0, 1, 0, blah, blah, blah is 0, 1, 0, etc. Okay, so computing addition in this field is very easy. Let's have a look at multiplication. Now, since I've already introduced this polynomial notation, I guess you may already be able to imagine what multiplication looks like. So here I have an example where I multiply this first number here by a very small number, namely by 101 essentially. And I do this simply in the polynomial multiplication way. So I separately, for writing it down here, for the purpose of writing it down, I first multiply 1 times the top thing, that's written down here, plus x squared times the top thing, where x squared times this is simply shifting this thing, this thing here, 2 positions to the left. This is exactly what we have down here. And we XOR this together. This is normal polynomial multiplication. So if we do that, we get another polynomial. That's great, but this polynomial has a big downside. Namely, it has degree 9, which is larger than the degree we allowed for the polynomials in our field. So this doesn't fit in the data structure we defined. So we need to reduce it in some way. And this reduction plays a similar role as computing modulo the prime number does in the fields we already know before. So we need a sort of modulus, which will need to have some properties equivalent to the prime property of the modulus that we saw last week. And we will need to define, of course, what reduction means for polynomials. So as an example here, I've taken this is just the problem description. So as an example here, I've taken the modulus that is also used, for example, in the AES. But let's first define what reduction means. So if I take the result of my computation, some polynomial f of x, and I compute modulo some modulus polynomial m, then I get some result r. And what this means, this notation, is that the original polynomial can be written as some multiple of the modulus plus a remainder. And the remainder is in some sense smaller than the modulus. This is very similar to normal definition of modular arithmetic, right? We did a division with remainder, and the remainder was what we were interested in. It's the same here, but smaller now means that the modulus doesn't fit in here anymore. In other words, the degree of this here is larger than this. So smaller is here defined in terms of the degree of the polynomial. So as an example, this here is the modulus that is used in the AES. Now, how large does this modulus need to be? If I want to reduce everything down to a remainder that again fits into the original n elements, then the modulus must have a larger degree than that, so it must have n plus 1. So if the previous things had length 8, here we now need length 9 for the modulus, so that every result of the modular reduction fits in the smaller size. So here is the intermediate result from the previous slide, the first row here, and I'm now dividing it by this modulus here to get the result that I want to get. So let's do this. What do I usually do when I do a division? I try to see how often the divisor fits in the original input. So how often does x to the power of 9 fit into x to the power of 9 something? What, it should be off by 1. Oh yeah, it's x to the 8 here, of course, because 9 elements, x to the 8. How often does x to the 8 fit into x to the 9? Well, x times. Now I deduce x times the modulus from the original input, so minus shifted by 1 the modulus. I get some remainder as a result. But this remainder is still of degree 8, which is the same degree as this one here, not smaller. So I can reduce again. I can again ask how often does this fit into here? Well, it fits 1 time, meaning I can subtract it 1 times. And now as a final result, I got something of degree 7. So strictly smaller than the modulus, and also small enough to fit into our data structure. So this final result is the remainder of this computation. It's also the result of taking our multiplication result modulo the modulus. You will probably remember this sort of computations with polynomials from analysis T1, where you sometimes had to do a similar sort of computation in the course of integrating stuff, because there you also often wanted to rewrite a polynomial or to divide polynomials in order to have an easier representation. And this is also what we do here. So you should know the general procedure. What's new here is that we are now doing it with operations modulo a prime number, modulo 2 in this case, instead of over the integers. And this also means that the question of how often does something fit in somewhere else is answered slightly differently. Because if I have 2 polynomials of the same degree, I can't really say that one of the 2 is bigger than the other. Any of them always fits a certain number of times in the other. Where how often it fits is defined by these 2 top coefficients here. and by dividing one by the other using modular arithmetic. So this gives us a reduction rule, and this also is sufficient already to define how our multiplicative group looks like. So multiplication in our field is simply multiplication of polynomials and then reduction by a modulus polynomial. And this modulus defines what sort of field I am in. So for example, the AS polynomial is a polynomial of degree 8, which means it defines a particular finite field of 2 to the power of 8 elements. And computations in this structure happen in the AS in several places. I'll get to that in a moment. In the meantime, let me mention one more application where we need this division. Namely, we also need it when defining how to compute the inverse of an element. Because this is something we also need in a field, some sort of way to compute the inverse of an element. And we do this here in a very similar way as we did in the prime fields, namely using the extended Euclidean algorithm. However, instead of computing it with integers, we will need to compute it with polynomials. But otherwise, the rules are exactly the same. Okay, so where are these fields used in cryptography? First of all, prime fields, like the one you've already known before, are used for very large primes P in the classical algorithms such as DiffieHellman and DSA. They are also used as part of prime elliptic curves. So elliptic curves with prime characteristic. We also use the finite field with 2 to the power of something elements. So looking exactly like the example we saw before, where addition is XOR and the elements are bits. We also use this for large M, namely for M of the size that is approximately equal to log 2 of the primes here. So if I write the numbers here and here down in bits, they will have similar sizes for the same security level. And so instead of integer multiplication or integer operations here, modulo and integer, I have polynomial operations, modulo polynomial. And these are used in so-called binary elliptic curves. So prime curves and binary curves use a different underlying field. And as I've also already mentioned, they also have very important applications in symmetric cryptography. Usually not over such big numbers, but with small sizes. So two places where we've already seen that is in the AES. There we have a field with 2 to the power of 8 elements, meaning they fit exactly in 1 byte. So 1 byte is exactly one field element in AES. And we use both multiplication in this field. This is how the multiplication in mixed columns is defined, where if you remember, you have to compute things like 3 times something, and the 3 is actually the polynomial x plus 1 in the representation we saw before. And use the polynomial multiplication with the modulus I also showed on the previous slide. And for the S-box, we're actually using inversion in this field here. So what the S-box does actually internally, of course it's not implemented that way, but what it does mathematically is it takes the input and inverts it, and that's the output, plus some extra bit filling. Except when the input is 0, then it has to be mapped to 0 because 0 is not invertible. So this is a special rule in the S-box. It also appears in other places. So for example, 3 weeks ago, in the lecture on encryption modes, we heard about the Galois counter mode. And the Galois here is exactly the Galois field we talked about today. So there you saw this multiplication as part of the computation of the message authentication code. So there we had this figure with some circled pluses, which are XORs, and some circled times symbols, which are multiplications in a finite field with 2 to the 128 elements. So where each 128-bit block is interpreted as one field element, again with some specified modulus, which is written down in the standard. So what do we do with these fields? One of the things we do is we look at their so-called multiplicative group, because it sometimes happens to be an example of a cyclic group. So to understand what the motivation of a cyclic group is, let's now head back to simple groups like we had last week. For example, computing modulo 6. Notice it's not a prime number. And what we're interested in here is the question, what happens if I take the group operation and apply it iteratively to some of the elements in my group. So the elements in Z6 are 0 to 5. If I repeat the plus repeatedly to 0, so 0 plus 0 plus 0 and so on, that's rather boring. If I do this with 1, it's a bit more interesting. So if I keep adding 1 to the previous number, I will at some point reach 6, so 0, and at that point I will start looping the elements again. If I do this with 2, I start looping much sooner. With 3, even sooner. 4 seems to be very similar to 2, and 5 looks actually very similar to 1, except that I'm going through the numbers in reverse order, which makes sense because 5 is the same as -1. But in any case, we see that if I take an element, keep repeatedly applying the group operation, at some point things will repeat. Because at some point, because I have only a limited number of elements, at some point I will run into an element again that I've already seen. And starting from this point, of course, things will repeat because I keep doing the same operation. And what we are now interested in is, how soon does this looping happen? Also, is it possible to find an element such that when I loop through it, I actually generate all the numbers of my set? So in this example, 2 numbers satisfied this. And if a group has this property, namely if it has an element, G, the generator, which can generate any other number in the group as by repeatedly applying the group operation, then I call this group a cyclic group, because I can generate it by running in a cycle. And G is the corresponding generator. And this means that for every other element A, I can find some so-called exponent. Well, it's not a so-called exponent, it is an exponent, such that I can generate the element as my generator to the power of this exponent. And this is also the reason why the word order is used for 2 different things in groups. On the one hand, the order of a group is the number of elements in this group, whereas the order of an element is the smallest index or the smallest exponent, such that the element raised to this exponent equals 1, the neutral element. Now, why is this number relevant? Because as soon as I hit 1, I will start repeating, because the next element will again be a squared, and so on. So the order of an element is the size of the cyclic subgroup of the full group that it generates. And in particular, the order of the generator of a group is the same as the order of a group. So let's have a look at a number example, namely numbers modulo 10. And let's first look at this with addition. So this is very similar to the computation we've seen already. 0, if I keep adding it, loops very soon, namely after the first step, so its order is 1. 5 can generate 5, and 5 plus 5 equals 0, so it has order 2. All the even numbers can only generate all the other even numbers, because the modulus is also even. And there are a total of 5 such elements, so the order is 5. And almost all elements are also generators of this group, except the 0, because we saw 0 already. 0 has a smaller order. And finally, the full group is also generated by some elements. So these here are the generators of this additive group. And they all have order 10, just like the group. Now, the interesting thing is, if I look at a different group with the same number of elements, for example, notice that here we're looking at additive groups modulo 10. Now let's have a look at a multiplicative group modulo 11, which has the same number of elements, because we need to kick out the 0. So you will notice that the picture hasn't actually changed from the previous slide, except that we renumbered the elements. And we also have exactly the same structure here, except that we have different elements in it. And this is not by accident, but actually these different groups of the same size have the same so-called subgroup structure. So these are two different groups. This will now allow us to define a specific problem with respect to the elements of this cyclic group, and specifically with respect to the generators here, namely the discrete logarithm problem, which says the following. So the challenge here is, given a prime number p, which is the modulus, and given a generator of this group, so a number that generates all other elements, plus some challenge element y, what we're supposed to do to solve this problem is to find the correct exponent, so the correct x, such that the generator to the power of this secret x equals the challenge number y. If G is a generator, such an x must exist because G generates all elements. And the challenge is only to find out which element that is. And so this is the definition for the specific case where the group is the multiplicative group modulo p, but we can also define the generalized discrete log problem, which is the same problem but for any group and its generator. And again, we write it as p to the g to the power of x, assuming that we denote the operation of this group by multiplication. If we would not need to denote it by addition, this would look a bit different, namely, assume we would be talking about the additive group modulo p. Then applying the group operation iteratively, so g plus and so on plus g, is actually the same as multiplying g by the scalar x, where x is the number of times I apply the group operation. So if I try to solve the discrete logarithm problem in this additive group, I'm actually simply trying to solve this very easy equation here, where g and y are given and we want to look for x. This is of course pretty easy because I simply can multiply both sides with the inverse of g and I will receive x equals y times the inverse of g. This immediately gives me my correct solution x without having to do anything more complicated than inverting an element, which, as we've seen, can be done very efficiently. What this means is that the discrete logarithm problem is not generally a hard problem. In particular, it's not hard in some groups, like for example the additive group modulo p. However, there are other groups where we don't really know how to do this step here. And one of these is the multiplicative group modulo p. So there we believe that the discrete logarithm problem is actually hard to solve. Okay, how hard is it? Of course, we measure that by having a look at what the performance of the best algorithms that we know for solving it is. So what are some of the algorithms that we know? The first three that we know actually have pretty much the same complexity. The first of them is the so-called baby step, giant step algorithm, which actually takes advantage of something related to, again, the birthday paradox, in order to find a correct solution in O of square root of the size of G many elements. So let's quickly have a look at this runtime here. What would be the brute force runtime? The brute force runtime would be to try every possible exponent, and there are approximately size of G many possible exponents. So the brute force runtime would be O of size of G, so order of G. But if I can do a sort of birthday paradox, which in this case happens by dividing the X into two parts and trying to find matching two parts using a sort of birthday attack, this gives us this square root in the runtime. There's also another algorithm, which is, to make things confusing, again named after Pollard. So it's not the Pollard p-1 factorization that we saw last week, but it's the Pollard row factorization algorithm, which is actually related to cycle finding. So you remember this row, we already saw it in the lecture on hash functions, where we had a look at this tortoise and hare algorithm. And this does something similar. So again, you can see a bit the idea of the birthday paradox in here. And for this reason, it also has a similar runtime. There's one other algorithm, the DiffieHellman algorithm, which has a more complicated looking runtime, but it's actually not that much more complicated. The main difference is that it also has the square root factor in it, but it's not with respect to the size of the group, but with respect to the size of the largest prime factor of the group. So for this algorithm, the runtime actually depends on the factorization of the size of the group. And if this has very, very large prime factors, then the runtime of this is essentially the same as up here. But if all of the prime factors are pretty small, meaning we have small subgroups in this group, then this algorithm is a bit faster. But as soon as I choose a secure group where here I have only large, or at least some very large prime factors, this algorithm isn't that much faster. And essentially we have this square root factor in all of them, which would mean that to achieve a certain security level, we need to approximately double the bit size of the security level in order to get the size of the group we need to work in. So for example, for a 128-bit security level, we would need a group with approximately 2 to the 256 elements. The bad news is, these are not all the algorithms we know, there is one more. And this algorithm is a lot faster. It's called the index calculus or sieving algorithm, and it's related to the sieving-based factorization methods, which we didn't explain last week, but I mentioned them and I gave the runtime. And you will see that the runtime here looks pretty similar. I'm just noticing that I'm using a slightly different notation here. So instead, for example, of writing log, I write ln here, but it's the same natural logarithm. Instead of writing ln g to the power of 1/2, I'm writing a square root here, but it's essentially the same format as the runtime complexities we saw last week. And in particular, this is a sub-exponential runtime. These here are exponential with respect to the representation of elements in G, because the size of elements in G is log G, whereas this is sub-exponential, meaning we would need much larger elements than just twice the security level. And one important thing about this algorithm is that it doesn't work for all groups. It only works in groups that have something, that have a certain concept of prime elements, like prime numbers that generate all other elements. Which means it does work in the multiplicative group modulo p, meaning multiplicative discrete logarithm modulo p is less secure because we have a faster algorithm, but elliptic curves allow to build us groups where this algorithm does not work, only these ones work, meaning we have slower algorithms, so we can choose smaller smaller bit sizes for the same security level. But before we go into details on that, let's have a look at some algorithms. You will notice that all of them are actually based on a sort of common principle, which is also an algorithm in its own right, namely the DiffieHellman key agreement protocol from the 1970s. You may have heard about it already. In particular, we covered it in information security. It works as follows. So the goal of the protocol is for two participants, Alice and Bob, to agree on a shared secret key. And for this purpose, they each generate a private key. So Alice's private key is a number between 2 and p-2, and Bob's private key is a number also between 2 and p minus 2, both of them uniformly randomly chosen. These are their private keys, and their public keys, which they send to each other, are some generator of a group to the power of this element. So this scheme here needs some group with a generator, and it needs it to be hard to compute the discrete logarithm problem. Because if we solve the discrete logarithm problem of these public keys, we get back the private keys. And after exchanging these two, both of them can derive the same secret key by taking the number that they received from their communication partner and raising it to the power of their own private key. Because of the rules of exponentiation, both of these computations give the same result, meaning they both end up with the same shared secret key that they can use for using authenticated encryption or so to encrypt their data afterwards. So that's the basic principle, and we will revisit or see again this basic structure of having some private key, which is an exponent, and some public key, which is the generator to the power of the exponent, in several other schemes. Actually, the hardness of this problem, so while this algorithm can be attacked by computing the discrete logarithm, there is actually a more specific problem which might theoretically be a bit easier that we need to solve. Namely, what we actually want to do here is, given these two numbers here, we don't actually need to find the secret key, we only need to find the resulting shared key. So given alpha to the a and alpha to the b, what we actually want to find is alpha to the a times b. And this is called the DiffieHellman problem, DHP. So given these two messages, we want to find the secret key. There are some variants of this problem, like the decisional DiffieHellman problem, which is something like, given these two and given a candidate for this key, you're only supposed to decide whether this candidate is actually the correct result of this computation here. So you're even given a potential solution, you only need to tell if it's true or not. And this still seems to be very hard. And the belief is that the hardness of the DiffieHellman problem is essentially the hardness of the discrete logarithm problem. But we don't have any proofs for this. This is only the best known solution to solve the discrete logarithm. So this is a key agreement scheme. Let's see how we can build something else from it, namely an encryption scheme, using essentially these ingredients here. And the resulting encryption scheme is called the El-Gamal encryption scheme. And you see from the picture, it's actually quite similar. So if Alice and Bob want to talk to each other, more specifically, if Bob wants to send something to Alice, what Bob needs is Alice's public key, which is constructed the same way as before. And Bob also generates his own private key and sends the corresponding public key. However, he doesn't have a long-term private key here. This is only a so-called ephemeral key, so it will be thrown away after one encryption. And this is because the encryption that Bob uses is a very, very simple one. He simply takes the DiffieHellman key that he would receive from this DiffieHellman key exchange here and multiplies it with the message. So he sort of masks the message using this secret key here. And this is the ciphertext that he sends to Alice. What Alice does is she derives the same secret key based on this one-time public key and her long-term public key, or private key, of course, you will need that, and use this to compute k. Then she can compute the inverse of k modulo the modulus. And of course, by taking this here and multiplying the inverse of k on, the inverse and k cancel out, and what remains is only m. So she decrypts the ciphertext by simply multiplying the inverse of the key she derived onto C. So this is a very simple encryption scheme, where essentially this is the actual encryption scheme, And before we do a sort of one-time DiffieHellman key exchange, because Bob's key must be used only once. Otherwise, if Bob reuses it, then information from this multiple ciphertexts can be combined to derive things the attacker shouldn't know. So unlike things like RSA, here we actually have some parameters which all users of the system can share. For example, the modulus, the prime number, can actually be used by everybody worldwide if people would like. Same thing is with the generator. Everybody could actually work with the same generator and wouldn't harm the security of the system, except for allowing something like multi-user attacks. But if you target an individual user, this is not weakened by using shared components, which can be standardized. There is, of course, a very, very big advantage to this compared to if you think of RSA. In RSA, every user had to generate their own secure prime numbers, which is a very complicated process because you need to look out for many potential weaknesses. And everybody had to do that, which costs a lot in computation time and is very error prone, so it often goes wrong. Whereas in this case here, the hard stuff, namely coming up with a good prime number P and a good generator, this only has to be done once, and then everybody can use the parameters. And what people need to come up with themselves is only a random integer in a range, which is a lot easier than generating a secure prime number in a particular range. So the effort of key generation is a lot lower here. I already said that we have this sort of temporary private key here. This also serves as a sort of randomization. So if Bob would send the same message to Alice twice, he would each time generate a new ephemeral key, meaning the ciphertext will also be different both times. So somebody who observes the communication wouldn't be able to tell that the same ciphertext, the same plaintext has been sent twice, because the ciphertexts will look different because of this randomization. So this means that we don't need a complicated padding scheme like we had in RSA with extra randomization and so on, but we can use a lot simpler padding scheme that does not introduce extra randomness. But of course, we must be careful to not reuse this randomness here. So we do need a secure random number generator for each encryption. And this is not only like in symmetric schemes where we must be sure that we generate nonces that don't repeat, but here we actually need to generate secret numbers because we need to generate a fresh private key every time for every encryption. This is unfortunately a big downside of this scheme, because it's also something that can go wrong. You also notice that to send something, Bob actually had to send two elements, the ciphertext itself plus a temporary public key, meaning that the ciphertext size here is larger than the plaintext size. So this is a certain inefficiency. Okay, so this is in any case an encryption scheme that is based on the same ideas as DiffieHellman. We can also make this into a signature scheme, but this is unfortunately quite a bit less elegant. Let's have a look at it anyways. So the key generation, I've now written it down in a similar notation as last week. The key generation phase is very similar as before. So if Alice wants to do signatures, she needs to generate a private key, which is an integer in the range 2 to p-2. And she derives the public key from it in the same way as before. So these two steps correspond to the first line in the picture before. Now for signing, here comes the first ugly part. She needs to compute a signature that consists again of two parts. The first part looks very familiar. It's simply a temporary private, the public key for a temporary private key. So signing here is also a randomized process. This is very different from the RSA signatures, the textbook RSA signatures. So Alice has a long-term private key and a temporary private key for which she generates the temporary public key. which she publishes as part of the signature. The other part of the signature, you will notice, is a computation modulo p minus 1. This probably means that the number we compute here will be something that will be used in an exponent later on, because in exponents we compute modulo p minus 1. And what this number here is it first involves this number r in some way. This is the first thing that I personally find inelegant, because here we have some computation that happens on the ground floor, modulo p, and afterwards we take this number and plug it here into the exponent. I personally find this ugly, because it sort of mixes things that shouldn't be mixed. But it does serve the purpose of integrating this public key as part of the signature here again, so that this part here cannot be changed out. We also need to involve the private key somehow, and we of course need to involve the message, or more specifically actually the hash of the message which comes here. And we're now essentially masking the this message here with a secret value, or this hash with a secret value, which depends on the long-term private key and on the short-term public key. And finally, we also fit in the short-term private key as well. Otherwise, the whole computation here would only depend on the short-term public key. This wouldn't make sense. And the verification then works as follows. So we need to essentially test whether the public temporary key given here and the hash of the message we received are compatible with this formula here. And to do this, we take the temporary, the long-term public key and raise it to the power of r, which is the second ugliness. So again, we bring this thing which was something on the ground floor onto the first floor, so in the exponent. But we also keep it here and raise it to the power of s, where s is the other part of the signature here. So this magic exponent we computed. And if you now fill in this number here for the s, and you evaluate the r here, and you do some exponential arithmetic, which is simple, but involves lots of multiplications, which is why I have not written it down here, you essentially get as a result exactly alpha to the power of the hash of the message. So we're trying to essentially remove this masking part here with these computations here in the exponent, so that we are only left with this value here in this exponent. If you don't believe me that this works, I suggest you just try it out on paper. You will manage in a few minutes, but yeah, it's not very beautiful or elegant. Okay, so what are some of the security properties of this signature scheme? First of all, like before, we don't directly apply it to the message for several reasons. First, to prevent a so-called existential forgery attack. So being able to come up with a value of m that fits and the corresponding signature so that they fit together. And the second reason is a practical one. If the message is long, we don't want to fit all of it into our group here. So instead we compress it down to a smaller value that fits in the group by hashing it. Unlike RSA, we cannot recover the message or the hash of the message from the signature directly. What's absolutely crucial is that this temporary private key is never reused. I already said that for the El-Gamal encryption scheme. I'm saying it here again, and here it's also very easy to show why it mustn't be reused. And this is something that you may already know from last year's InfoSec exercises where something similar appeared. But let's have a look. What would happen if somebody would reuse the same temporary private key to sign two messages? This would mean that if we look at the exponents in the previous formula, so if we look at this definition here and rewrite it a little bit, so bringing k to the other side and adding x times r to the other side, what we would get is this. The first message equals the secret long-term key times the temporary public key plus the temporary secret key times something that depends on message 1, namely, this value here. So this second half here, this S. And almost the same thing will also be the case for the second message. The only value that is different is going to be the second part of the signature, so this S, whereas the R is going to be the same if the same temporary private key is used, because it only depends on that. Now we have two equations with a very similar format. We can subtract them from each other, and this part here will cancel out. So if I subtract m1 and m2, then the x times r will cancel out, and what I'm left with is the temporary private key times the difference of the two signatures, which means we can recover k from this formula, the temporary private key. Now that itself is not worth a lot. However, if we look at the original equations again, now if we recovered this key, we now know S because it's public, we know K because we recovered it, we know R because it's public, and we know M because it's public. So the only thing we don't know is X, and we can simply rewrite the equation and solve for X, meaning we would get the long-term private key from this, simply if the temporary key is reused only once. Okay, so this signature scheme is usually not used in exactly that shape in public applications, but in a slightly different format. I'm not going to go into details on this. This is the so-called digital signature algorithm. It's essentially the same as before. The major difference, so there are some differences in the details, but the major difference is that the results of the signature after being computed are again reduced modulo another smaller prime number q, which divides the p minus 1, which is the order of the multiplicative group modulo p. So this is the size of a subgroup of the multiplicative group. So all the computations that are done are compressed down into a smaller subgroup. And the purpose is that I have afterwards smaller signature sizes. That's the main advantage, plus some other minor changes. What we receive as a result, if we look at the security level, is the following. So for this DSA algorithm, the size of the main modulus P is essentially the same as for RSA for a particular security level. So for example, for 128-bit security, we get a 3000-bit key. However, this Q can be a much smaller prime number, namely only twice the security level. And meaning this is the size that we also saw previously that we would like to have for this sort of schemes. So DSA doesn't quite manage to bring down the key size and the size of all the computations to this level, but it does manage to bring down at least the signature size, which is 2 times this. So the signature in this construction is the size is 4 times the security level. This modification also has some other advantages. In particular, some of the values can be pre-computed before actually seeing the message. And something that I would say is a downside, but that people at the time found to be an advantage, is the fact that this DSA scheme cannot be easily changed into an encryption scheme. So unlike RSA, where the signature and the encryption scheme are very, very similar, this is not the case here. So you can't easily make DSA into an encryption scheme. And why was this seen as an advantage? This is because for a long time there were export restrictions on cryptographic schemes, but only on some cryptographic schemes. So it was not allowed to export from the US any secure encryption schemes or hardware that implements secure encryption schemes, but it was allowed to export secure signing schemes. And since this can only be used for signing and not for encryption, it could be exported. There are some other performance downsides, like for example that verification of the signature is the slow operation here, whereas signing is a faster operation. And usually a signature is only computed once, but potentially verified many times. So we usually want it the other way around. It's better if verification is the cheap operation. Okay, so this is a sort of intermediate summary on the cryptography based on finite fields. We see with some trickery we've managed to reduce some of the bit sizes, but overall we're still stuck with these huge sizes, meaning large keys and meaning large signatures and so on to be transmitted, large ciphertexts and so on. And the solution to this, or the currently popular solution to this, is elliptic curve cryptography. So the motivation here is what I've already tried to sketch, the fact that so far for what we've seen for all the arithmetic over finite fields, we saw that there are sub-exponential algorithms for solving the hard problems. So we have sub-exponential factorization methods, and we have index calculus, which is a sub-exponential discrete log algorithm, but it doesn't always work. And the other methods we know for the discrete logarithm are all of exponential runtime. So what we're looking for is a different kind of group where we are unable to apply this index calculus method, because it doesn't have anything like a prime factorization of elements, leading to a different representation of elements. And the candidate that we have for this, where we have no clue how the index calculus should work and can't imagine that it would work, are these elliptic curve groups. So what are those defined like? What's an algebraic curve? Because elliptic curves are a type of algebraic curve. You already know some algebraic curves from your high school times, I guess. Namely, when you had a look at geometry, you probably learned some equations like the equation of a circle, where you take the x and y coordinates of the points, and you notice that if you, for example, look at a circle with a radius 1, then all the points on the circle satisfy the equation that x squared plus y squared equals the radius squared, so 1. Which you could also write as a polynomial equation, so as a function of the coordinates x and y, which equals 0. And the function in this case is x squared plus y squared minus the 1. So this needs to go to the other side. So the circle is an example of an algebraic curve. And it's defined by this sort of algebraic equation with some unknowns which correspond to the coordinates. An ellipse is a very similar, closely related kind of algebraic curve, which looks a bit more complicated, so it has a bit more efficiency in here, because it also has more degrees of freedom than just the radius. So it also satisfies this sort of curve. And despite its name, an elliptic curve is not actually related to ellipses, so this is maybe a bit misleading, but it's a similar type of curve. Namely, it's also defined by a polynomial equation of the coordinates x and y, which is supposed to be 0. You will notice that the equation is a bit more complicated, so it involves an x to the power of 3 here in this example. And the shape also looks quite different. So this is one particular example which corresponds to this curve. And by changing the coefficients here, you can change the shape of the curve a bit. Just like you can change the shape of an ellipse by tweaking with these coefficients here. But all the points that satisfy one of these equations of this particular structure here are called an elliptic curve. And this structure, so this particular function of x and y that is supposed to be 0, this is the so-called Weierstrass form. And this Weierstrass form has several parameters that you can change to tweak the appearance of the curve, which are denoted here by AI to A1, so A1 to A6. So these are constants that define what the curve looks like, and the x's and y's are the coordinates. And the elements of the curve are then all valid combinations of x and y. And the x and y's, as well as the coefficients, are elements of some field. In cryptography, of course, we're interested in finite fields for this purpose. So an elliptic curve is nothing else than a set of solutions to some equation. There are some simplifications possible depending on which field I'm computing in exactly. So if I know that I'm working either in an infinite field like the real numbers or the complex numbers, or if I'm working in a prime field with p to the power of n elements where p is neither 2 nor 3, then I can simplify this complicated equation to this one here by doing some coordinate transformations. We don't care about the details. I'm just saying here that it's possible and that you often only see this simplified representation, which only has 2 parameters left, plus some additional conditions that A and B need to satisfy. So not all A and B actually give a valid curve. So we talked earlier about the field with 2 to the power of something elements, which is not covered by this simplification. For this, we have a separate form, which you notice is a bit different from the above. So for example, it includes the term x times y here. But it's still a lot simpler than the general form here. So these are the 2 types of curves that you will often see in cryptographic applications. They aren't the only ones, because there are a number of different clever coordinate transformations you can do, which have some computational advantages, but these are the basic forms. So to get a feeling for this, let's have a look at some pictures. So here, these are pictures for elliptic curves over the real numbers. So we're using the simplified format, up here, that I defined on the previous slide, and plugging in different values for the 2 coefficients A and B. So this one here is for A equals 0 and B equals 0, and in this direction or in this direction I'm increasing either one of the numbers. You will notice that there is something in common to all of these. I had to cut them all off here at the top right and the bottom right, because they would continue infinitely far in this direction. So they all have this general slight curve form. Some of them have this sort of bubble here in front, and this bubble may also disconnect. So you may have a shape where you have 2 components, small bubble and the curve, which looks very similar to the curve without the bubble. In the nice cases, all of these shapes are smooth, so they are differentiable at every point. This means that the particular case of A equals 0, B equals 0 is not a nice curve, because you can see it has a point here, a singularity, a point where you cannot differentiate. And such points or such curves are not counted as useful or real elliptic curves. So only the nice smooth ones are actually called elliptic curves. And to see whether such a singularity exists, you actually don't have to look at the picture. You can derive this from the coefficients A and B. And the way you find this out is by computing the so-called discriminant of this curve. And for this particular shape of curve we saw on the previous slide, the discriminant is defined as follows: minus 16 times 4a to the power of 3 plus 27b squared. I'm not deriving here why it looks that way. If you're interested in that, I can give you some literature recommendations. In any case, what this discriminant tells us is some basic properties of the curve. If this value is negative, then we have the case that we have a curve of 1 component, so no bubble, no separate bubble. If the discriminant is positive, then we do have a separate bubble, And if the discriminant is 0, then the curve is not smooth because the bubble is sort of currently in the process of disconnecting. So you either have a point like here, or you can have a loop like in this example here, where you again have a non-differentiable point here in this intersection, which is called a singularity. And curves which don't have a singularity are called non-singular, and these are the ones we actually refer to as elliptic curves. So we've now described what the set of elements look like that we're interested in. What we haven't discussed yet is what the operations look like that we're working with. And before we define the operations, let's first briefly talk about whether we've already found all the elements we need. And it turns out we actually have not. So there is one extra element we need to add to this curve in order to make it a valid group. And this special element is actually the neutral element, which we say is a special point up at infinity. So it's infinitely up along the y-axis. We will see why that is relevant in a moment. Next, let's have a look at the inverses. So this is a bit counterintuitive. I'm now defining the neutral element and the inverse before I'm actually defining the operation. Usually this doesn't make sense, but in this case they're easier to describe. So the inverse we simply define by mirroring the point on the x-axis. This, as you can guess from the previous pictures, seems to always be possible because it looks like the curves are always symmetric. So you can always mirror them at the x-axis to get the other half. And if you look at the formulas, you can actually see that this is the case. Because if you look at the formula here, the y-coordinate only occurs in its square form, which means minus something and plus something give the same result, meaning they're both solutions for the system if one of the two is a solution. So this means that our curves actually must be symmetric, which means the inverse is always well defined. In the case where we have this value here with y-coordinate 0, this point is its own inverse. Now we can finally come to the definition of the addition, which will give some reason to these choices here. So addition is defined as following. This is the so-called chord rule. So to add 2 points on the curve, P and Q, what we do is, in the geometric interpretation, is we draw a line through these 2 points. And because of a magic property of the elliptic curves we defined, again, if you want to know more details, I can give you some reading recommendations. So this line will intersect the curve in exactly one more point. This is a guaranteed property that we have. We take this extra point where the line intersects the curve for the third time and mirror it along the x-axis, or well, we again invert the y-coordinate just like we did for the inverse. And we define that this resulting point is the result of the addition P plus Q. So why does this make sense for the neutral element, and why does it make sense with respect to the inverse? Let's first have a look at the neutral element. So let's take the point P and let's see what happens when we add the neutral element to it. What we would like to get is we would like to get again P as a result. So in this geometric representation, I now have to draw a line through P and the special point. Now the special point isn't actually part of the picture, but of course you can imagine if I draw a vertical line, it will connect with the special point somewhere at infinity. This connection is actually just a vertical line through P. Now this does intersect the curve in exactly one more point, namely at the inverse of P. This would give us this intermediate result here. And now to get the final result, I mirror it, leading me back to P, so I again get P as the original result. So this neutral element is actually neutral in the sense that adding it doesn't change the point P. And you can now also follow that if I add a point and its inverse by drawing the vertical line through them, finding the extra point that is on the same line, which on this vertical line is only the special point at infinity, meaning the intermediate result is the special point at infinity, but this point is self-inverse, so reflecting it along this axis here gives us the same point again, so the result of this addition will be the neutral element. So at least what we've defined so far somehow fits together. There is now one case that we haven't covered yet, or where this rule doesn't exactly apply, and that is if we try to add 2 points which are actually the same point. So if we compute p plus p, so this is also called doubling for obvious reasons. In this case, what we essentially do is what is essentially the limit of what we would get if we move the second point q closer and closer to p, because the closer we move this point here, the closer this chord actually becomes to a tangent in the point p. So this is exactly what we do for doubling. We draw the tangent line in this point, which will intersect with the curve in exactly one more point. This is our intermediate result. We mirror it again and get the result of the computation. We can also summarize these computation rules in one general term. And the summary is that whenever I draw a line that intersects the curve in 3 points, or that has a double intersection, meaning a tangent touching point in one of the points. So whenever, let's take the simple case, whenever I intersect it at 3 points, then the sum of all these points is 0. You can apply these to everything the summary to everything you see here. You can of course, so if of course in cryptography you don't do any of these picture drawing steps, instead you translate all of this into general formulas. So for example, intersecting things means plugging a representation of the one into the other equation and then solving that. If you do that, what you get is something like this. Please don't learn it by heart, but let's have a closer look at what it looks like. Computing the subtraction looks very easy. This is simply flipping the y-coordinate. If we add or double something, you will notice that, oops, sorry, I changed the light color. This is ugly. Let's get back to the normal one. I think this is the normal one. Okay, so what you do as an intermediate result is some sort of division by the difference between the two x coordinates, which in case of doubling p isn't really possible. So we have a slightly different format here. So you have some divisions in there and some doubling, otherwise only simple field operations like subtraction, and for the y-coordinate some multiplication instead of doubling. And so this has two versions here. The one is for the case of infinite fields, as well as fields with a prime characteristic which is not 2 or 3. And this is the special case for binary fields. Okay, so these are the general formulas which are implemented in some form when you implement the curve in practice. You will also notice that the nice pictures so far have all been for real curves, and that is because the pictures for finite fields unfortunately look a bit less attractive. So here's a comparison. This is a particular curve, namely y squared equals x to the power of 3 minus 2x plus 1 over the real numbers. You see a nice symmetry, you see a nice smooth shape. And here's the same curve, but over the field with 89 elements. So Z89, where 89 is a prime number. What I've done here is, so usually you would get an x coordinate from 0 to 88 and a y coordinate from 0 to 88. However, in order for us to be able to see the symmetry more nicely, I've map the part from 44 up to 88 down into the negative equivalent values. So for example, the things slightly below the 0 line here are somewhere around 87 up there actually. But of course, this is just an alternative representation of the same numbers modulo 89. So you see the symmetry preserved, but otherwise it unfortunately doesn't look very clean and easy to understand. But this is of course the point. We want something where it's hard to see any particular structures, even with the very limited number of bits that we have available and use. What this means for a finite field is, of course, we have in total a finite number of possible combinations x and y, and some of them satisfy the equation. One of the questions that is now of course relevant is how many points are there in this picture, or in general, because this defines the size of our group. The number of points here is the order of the group we just built. And the order of the group is relevant because a larger order means that the discrete logarithm problem is harder to solve. So how many points are there in there? This number is called the order of the group. And to find out how many there are, let's look back at the picture and also at the formula. You will notice that as soon as you pick one x coordinate, the right hand side of this equation is fixed. The left hand side then says our corresponding valid y coordinates must satisfy y squared equals this result here. Now this is a quadratic equation, meaning there is anywhere between 0 and 2 solutions for this. Most often 0 or 2. In some cases, when y squared equals 0, we have exactly one solution. On average, there is going to be approximately one solution for these equations, which means that the exact number of points of the curve is approximately the same as the number of points in the underlying field, but not necessarily. And more specifically, there's a theorem that quantifies this, Haas's theorem, which says that n, the number of elements in the elliptic curve, equals q, which is the size of the field, plus 1 minus t. So this 1 minus t here gives us the deviation between the size of the field and the size of the curve. And this discrepancy, this t, is relatively small. So the extent to which it deviates is at most 2 times the square root of q, meaning it's somewhere in the vicinity of the same number of points. But so for simplicity as an approximation, you can expect that they're roughly the same. Finding the exact number of points is actually not that easy for a given curve. So you need dedicated algorithms for that, such as Schoff's algorithm. What can we say about the order of points on the curve? This is defined like before. So when we have a point on the curve, we can again ask the question, how often do I have to add the point to itself? Because adding is the group operation here. How often do I have to add the point to itself in order to generate the neutral element, which we denote by this calligraphic O? And the smallest number that satisfies that is the order of this element. In other words, this is also the size of the subgroup generated by P. So if P is a point with a very large order, means it can generate more numbers, means it's more suitable as a base point in elliptic curve problems, in discrete logarithm problems. So that already leads us to the discrete logarithm problems. This is now a rephrasing of the general discrete log problem that we saw in the beginning of the lecture for the special case of elliptic curves. And it goes as follows. The challenge is you're given a base point P, which hopefully has a large order. You're given a challenge point Q, and you're supposed to find this scalar here. Scalar meaning it's not a point, it's a number that tells you how often you have to apply the group operation to the base point, so p plus and so on p, in order to generate the value q. What can we say about this? We can see that the problem looks very similar as before, except that we are always using this addition instead of the multiplication in the notation. And we can also again separate these two rules. This k is what used to be the exponent in the previous schemes, whereas the p plays the role of the basis. And this means that we can translate some of the previous algorithms that we saw, such as DiffieHellman, by replacing all the base values by points and all the exponents by scalars like this. And we will then get cryptographic problems which are based on the elliptic curve discrete log problem instead of the normal discrete log problem. And the great thing is, again, that as far as we know, for most of the curves we can generate this way. The fast index calculus method for finding the discrete log doesn't work. Here are now some examples for this translation process. So on this side here, we see the original classic DiffieHellman, and on this side here, we see the elliptic curve counterpart. You see that exponents, which are natural numbers in the original, remain natural numbers. But the base point we use them for is now not an element of z modulo p, but an element of the group, so a group point, which we also call a base point alpha. And the public key, instead of alpha to the power of the private key, is now the private key times the base point. Again, because it's addition instead of multiplication. For Bob's key, the same thing. And for the final derivation of the key, so instead of doing two exponentiations here, we do two scalar multiplications here. So first number a times point alpha, and then the result of the point of this here, we take the scalar b times this point to get the final result, which is also a point. So whereas we got a number as a result here, the resulting key k will be a point here. So to match it back to a bit string, we can do something like hash it or something like that. Because if we just take the two coordinates, we will notice that they are not uniformly distributed. Because we saw already for a particular x, there are only up to two valid values of y. So the whole string is not a uniformly random string. We can also do the same thing with more complicated algorithms like the DSA algorithm. Again, doing the same sort of replacements. Exponentiations by scalar multiplications, and additionally for everything where we do a computation modulo q in the original DSA algorithm, we first take the x coordinate and then reduce that modulo q in the elliptic curve version. And here we also run into some issues when we try to translate, for example, the El-Gamal signatures, because of these mixture of using elements both in the exponent and as a basis. So there we need to be careful. This is then harder to translate. Some final notes on implementing this efficiently. First, on the representation of the points. When we looked at the computations, I noted that these computations do involve some division operations. So for each point addition, you needed to compute two divisions. And dividing things is quite a bit more expensive than multiplying things. This makes sense if you think back of the exercises today. Every time you had to compute a modular inverse or divide things, you needed to run this extended Euclidean algorithm. Now there are efficient implementations of these steps, but it's still a lot more costly than just multiplying. So getting rid of these inversions would be very valuable to speed up the computation time. And this is why implementations often use an alternative representation. So instead of having a y and x coordinate, they write down three-part coordinates where we have x and y plus an additional value z that represents or that collects what we should have divided our x and y by. And if you look at the formulas we saw earlier, you will notice that we can use the same z essentially for x and y, but we need to rewrite the equation systems a bit in addition. So what we get if you do this translation is we have larger point representations because we have an extra coordinate. But the good thing is that divisions are essentially for free, because if my algorithm would tell me to divide x and y by some value z, instead I multiply this value z to this third coordinate, and I collect my divisor in there throughout the computations, instead of actually doing the division. And these are then called projective coordinates, whereas the originals are called affine coordinates. And this also has some mathematical background, namely so-called projective spaces. There are tons and tons of other optimizations that you can do. Many of them have names like curves, like there are Koblitz curves and Montgomery curves and Edwards curves and whatnot. They're all two different sorts of things. Some of them describe a particular mathematical property that a curve has. Some of them describe a particular coordinate transformation that you did in order to make the addition computations on the curve more efficient, or only for specific prime numbers, and so on. So all of these have different goals in mind, but you will very often read some name plus curves to refer to a particular type and a particular representation of curves. These curves I mentioned already need to be secure. One of the things that tells us whether a curve is secure against certain attacks is the so-called trace of Frobenius. This is the number t that we already met before, and it describes how different the size of the curve is from the size of the field. And if this has very special values, then we have weaknesses. For example, if t is exactly 1, meaning the number of points on the curve is exactly the same as the number of points in the field, then this is called an anomaly. So the curve is anomalous. And if this is the case, and if additionally we're talking about a prime field with exponent 1, then this means that the curve is weak, because there is a particular algorithm that can allow us to subvert the security properties. There are also other cases. For example, if t is a multiple of the value p, where the q here, the size of the field, q equals p to the power of something. So if the m here is very large and the p is very small, so that it works out that t is a multiple of it, then E is called a supersingular curve and also has some weaknesses. So generating a good curve is hard, but it only has to be done once for a particular system setup. And then many users can use the same curve. To be secure, it must be sufficiently large. It must be possible to find some good base points, meaning points of large order, to replace the generators we saw in the previous curves. Here we can't often guarantee that we have generators, but we need some points at least with some large order. And we don't want any of these additional weakness properties to be present. So to summarize everything that I've talked about now, the big advantage of elliptic curves is that it's a different kind of mathematical group where we don't know how to apply sub-exponential algorithms such as index calculus. This means that we only have available the slow algorithms for solving the discrete logarithm, and it means we can use smaller key sizes. And all the values, all the fields underlying it can also be smaller. So here is a table of recommended key sizes for the different structures. So for example, for 128-bit security, the recommendation for RSA is 3000 bits. For finite field-based discrete log crypto like DiffieHellman and DSA, it's also 3000 bits. But if we use elliptic curves, we can reduce this to 2 times the security level, 256 bits. This means the keys are small, the signatures are small, and all the computations are potentially faster because the field also only has, so all the numbers you work with also only have 256 bits instead of 3000 bits. So this is the big advantage. We can easily adapt most of the algorithms we have to elliptic curve versions. In particular, for DiffieHellman, it's very, very easy. One big issue with this and one big discussion point is who do we trust to select the curves? Because we said it's great, we only need to do it once, and we need to check that there are no weaknesses. And if we now allow an entity to select these curves and we mistrust them, we think that they have more cryptanalytic knowledge than publicly available, and they could know about some weaknesses, they could build that into the curve, and the public doesn't know about it because they don't know the corresponding attack, then of course we would have an issue. And one of the ways that people try to work against this is by trying to generate the curves in a very transparent way. So they say we want exactly these properties to hold, and then we generate the corresponding coefficients of the curve in a so-called nothing up my sleeve way. So nothing up my sleeve numbers are a term inspired by magicians, which often hide stuff in their sleeves, which is why real magicians often run around with shorter sleeves like I do here, where you can't hide anything. And the analogy for crypto would be that you try to generate the coefficients in the curve, the A and B, in some way that has a very low entropy. So that where the argument here is that if I knew a special weakness, I would probably know that it only works for some curves. So there are weak curves and strong curves. And I would need some sampling in order to actually hit a weak curve. And if I now have only very small bit of entropy that I use, then I don't have the freedom to reach a weak curve. So for example, what you could do is, as a designer, you could hash your name and let the bits of the hash output define some of the parameters of the curve, so that you have very little freedom or wiggle room. And this is then a lot less suspicious. This is something we also see in the design of block ciphers, for example, when, for example, defining an S-box or something. Then we also should have a reasonably clear and rigid explanation of where we got these parameters from, and what properties they should satisfy, so that we don't have the freedom to explore a large set of numbers and pick the few weak points in it, of which we know some secret weakness. Okay, I think we will have one more mention of curves and weaknesses sometime at the very end of this course, when we talk a bit about vectors. I don't know if this lecture is actually part of our plan for this year. We will see. In any case, this was the last lecture that you heard from me for quite a while, because next week Daniel Kahles is going to continue with the lecture instead of me. So I will still do the exercises next week probably, but I won't do the lecture probably until somewhere near the end of the term. There are some lectures where we haven't quite decided yet who does them. Okay, that's it from my side. Do you still have any questions at this point? That really doesn't seem to be the case. If you still come up with something, as usual, you can find me on Discord or also directly contact me by mail. In the meantime, I hope you have a great weekend and see you next week in the exercises. Bye!